So this is the last lesson of this very first unit. I'd say it's probably the first two units. Our first unit was essentially on all the atomic structure, and our second unit has been on all the reactions. So nuclear chemistry is the last type of reaction that we are going to study. And nuclear chemistry is very different from the reactions that we just studied. So we looked at things like single displacement, double displacement, combustion reactions, synthesis, and decomposition. Within all of those reactions, essentially what was happening was that we were creating different compounds by moving electrons. So we talked about ionic bonds and covalent bonds. By going through those reactions, electrons were being lost, gained, or shared in order to break apart atoms and then reform new bonds, new ionic or covalent bonds. With nuclear chemistry, we're no longer concerned about the electrons because the electrons aren't actually in the nucleus. Instead, we're concerned about what's happening inside the nucleus, which is where the protons and the neutrons are. So this is what nuclear chemistry is all about. So nuclear chemistry involves reactions that happen within the nucleus of the atoms, and all nuclear reactions produce some kind of radiation in the form of electromagnetic waves or particles. So in a previous lesson, we took a look at the electromagnetic spectrum. We saw that there was the visible light spectrum, and there were X-rays and gamma rays and all sorts of stuff like that. The gamma rays in there are the radiation that is formed during a nuclear reaction. And what we're looking at specifically in the atom is the nucleon. The nucleon is essentially the protons and the neutrons that are found inside the nucleus. Before we get into the actual reactions, we're going to take a look at different types of radioactive particles. So alpha particles are ones that you are slightly familiar with already because we have seen this in Rutherford's experiment, and we also just saw it in the last lesson about neutrons. Alpha particles have a positive charge. Specifically, they have a charge of 2 and they have a mass of 4. So beta particles have a negative charge and have very low mass. Positron particles have a positive charge and they also have a very low mass. And then we have gamma particles that have no charge and no mass. So the symbols for these, let's go over here. So we've got alpha particles, and then you may want to include this in your notes. Alpha particles, the symbol for that is He, 4, and 2. So this is written in standard atomic notation. This is the mass, and this is the charge. Okay, so here we have the symbol. We put here the mass and the charge. Another way that you will also see this alpha particle written is still with the 4 and the 2, but sometimes you will see the alpha symbol instead of the helium. These are both interchangeable. It doesn't matter which one you use. The next particle is the beta particle. So the beta particle uses either the beta symbol, and it has no mass. Okay, the mass, if you remember from that chart, was very, very small, so almost negligible. We call it 0, and it has a negative charge. Because it has no mass and a negative charge, it is very similar to an electron. So you can also use this symbol instead, either the beta symbol or the electron E symbol. Next we have a positron. Let's go here. So a positron is very similar to the beta particle. The only difference is that instead of having a negative charge, it now has a positive charge. And it can also have either the beta symbol or the E. And then our last particle is the gamma particle. And the gamma particle is the one that is the most dangerous and the one that we need to protect ourselves from. Gamma rays are present in all kinds of nuclear reaction. Every kind of nuclear reaction produces gamma rays, and then they will either produce alpha or beta particles as well. So the gamma symbol looks like this, and gamma rays have no mass and no charge. And there's no other symbol or way to draw that particular symbol. In terms of absorption, the reason why we need to protect ourselves from radiation is how it can potentially enter our body. So I'm sure you've all had an x-ray at some point in your life. If you haven't broken a bone and had an x-ray that way, you've probably gone to the dentist and had an x-ray in your mouth. When you go to the dentist, the x-rays that they use produce gamma rays. So the hygienist will often put, well, not often, they have to put on a very heavy vest on you. That vest is made of lead. And when they are actually taking the x-ray, the only person in the room is you. They leave the room in order to turn on the x-ray, and then they come back when the x-ray is done. The reason for that is how these penetrate your body. So alpha particles, the ones that are very similar to a helium atom, can simply be stopped by paper or clothing. So if you're exposed to that and you've got clothing on, it will not penetrate through the clothing. Beta particles are a little bit more dangerous. They will go through paper, they will go through your skin and your clothing. However, if your clothing is heavier, or if you are surrounded by wood, you can be protected from the beta particles. The gamma particles are the ones that can go through everything and can penetrate through all of this. What they cannot penetrate through is lead and concrete. So the vest that they put on you is very heavy because it is made of lead. They put it on your chest because they are protecting all of your internal organs like your heart, your lungs, your stomach, all of those things. Often in hospitals, you could potentially be in a room that has concrete walls to protect everybody as well. That's how dangerous these gamma rays are. When we are talking about nuclear chemistry, we also have to take into consideration something called half-life. So there are lots of isotopes that are used for medical purposes in order to actually help people, and they do emit radiation. The radiation is what actually makes them effective. So sometimes you may be given, if you're about to take a test like a CAT scan or an MRI, you may actually be given something to drink, and that drink in it has a radioactive isotope which images different parts of your body of whatever it is that they're trying to test. Those isotopes are going to be radioactive for a certain amount of time based on the half-life. So what is the half-life? A half-life is how long it takes for a radioactive isotope to be half of its radioactivity. So if we start off with 100% radioactivity, how long does it take to go down to 50%? There are some isotopes that could take seconds. There are other isotopes that take literally millions of years to decrease. Those ones are the dangerous ones. For medical applications, we definitely don't want an isotope that only takes a few seconds because you won't have time to do the particular test. So these isotopes may take a few hours or maybe 30 minutes before they decompose. If that's the case, you're usually in the hospital for that amount of time until the radioactivity decreases and you yourself are no longer radioactive. So this graph here shows what's happening. On the bottom here, we have the number of half-lives, and here is the percentage of the original isotope that's remaining. So our original isotope is 100% radioactive. After one half-life, it's gone down to 50%. After a second half-life, it goes down by 50% of that second total. So 50% of 50 is now 25. Now, of this remaining 25% of the molecules, we will go through half of that. That's 12.5, and eventually we will get down to something very, very close to zero. This will continue until it goes down to zero. So you'll see even after 4 half-lives, there is still some of that radioactivity present. Now, with all nuclear reactions, we do have to balance these as well. The balancing is a little bit easier than it was with the regular chemical reactions. So whenever we are writing these out, we always write them using the standard atomic notation. So that's where we have the element symbol, and then we put the mass number on the top and the charge or the number of protons on the bottom. When you are balancing on your reactant and your product side, the top numbers need to add up and the bottom numbers need to add up. That's it. So let's go through some examples here. Our first example is an alpha decay. Decay means that an alpha particle is going to be emitted. If an alpha particle is being emitted, that means it's going to be one of the products. So it's a loss of an alpha particle, and if you recall, the alpha particle is 4,2 with helium. So here we have a radioactive isotope of uranium. This is uranium-238. So a way that I can write this is U-238. This represents the total mass. When it goes through an alpha decay, one of my particles is always going to be the alpha particle, so 4,2 helium. The other particle is going to be whatever is left over. So right now, here's the answer to this question, but we don't actually know what it is. So how do I determine this? I just do a very simple subtraction. So let's do this over here. So I've got uranium, 238, and that was element number 92. This is an alpha decay. So I have the helium particle, and now I just need to do a simple subtraction. So I have 238 on my reactant side and 4 on my product side. So I will do 238 minus 4. That leaves me with 234. Okay, then I do 92 is on my reactant, 2 is on my product. I subtract those two, and I get 90. Now, to know which element this is, I know that 90 could represent my atomic number. So I find out which element has an atomic number of 90 on the periodic table, and that is thorium. Okay, so this is now a balanced nuclear reaction. 4 and 234 equals 238, 90 and 2 gives me 92. All done. So these are a little bit simpler to balance. Okay, let's do another example here. Determine the products of an alpha decay of radium-226. So we're not given very much information here, but we can easily figure this out. First of all, I want to know what the products are. So this tells me that radium-226 is one of my reactants. And I know it's an alpha decay because that's in the question. So let's go through here. Oops. Okay. So we have radium-226, and I know it's an alpha decay, so that means my alpha particle has to be on the product side. Now I'm missing some information about radium, this right here, so I need to find out what the atomic number of radium is. So if you look on your periodic table, radium is element number 88, so I will throw that in there. Now I just need to make sure that whatever is left over here adds up to what I have. So I've got 226 minus 4. That gives me 222. And then I have 88 minus 2, which is 86. I now go to my periodic table right here. I want to know what element number is 86. And 86 is element radon. Double check your work. 222 and 4 gives me 226. 86 and 2 gives me 88. So these are all alpha decays. Okay, so you can see what's happening right there. You'll notice here there's a different way of writing out the helium atom or the alpha particle. It doesn't really matter. The key thing to keep in mind is that when it's a decay, this alpha particle will always be a product. Okay, next one is a beta decay. In a beta decay, we are losing a beta particle. So a beta particle is the 0, -1 with either an E for an electron or B for the beta. Here I have an isotope of carbon, has a mass of 14 and an atomic number of 6. So this is carbon-14. When carbon-14 goes through a beta decay, one of the products is the beta particle, and then whatever's left over is going to be my other product. So going through this equation, delete this. Okay, so we've got 14 carbon 6. It's going through a beta decay, so we've got our beta particle. When you are doing beta decays, people always forget forget how to do math with negative numbers. This is a negative number, so please be very careful. We are not doing 6 minus 1. We're doing 6 minus negative 1. Okay? Let's take a look at our superscripts first. I have 14 on this side and 0 here. In order to balance it out, that has to be 14. So now what minus 1 will give me 6? That would be 7. So 7 minus 1 equals 6. Now I go to my periodic table. I find out which element is element number 7, and that is nitrogen. Okay, let's do another example. Determine the products of the beta decay of H3. So this is hydrogen. This is a special isotope of hydrogen. There are actually 3 of them. So there's hydrogen that has a mass of 1. There's hydrogen with a mass of 2, which is called deuterium. And then there's hydrogen with a mass of 3, which is called tritium. So I want to figure out what the products of this beta decay is of hydrogen 3. So here we take our hydrogen 3. You need to look on your periodic table, find out the atomic number. The atomic number of hydrogen is 1. So I will put that here. Because it is a beta decay, that means that my beta particle, I'll draw it in a different way just so that you can see it's interchangeable. I put in my beta particle here, and now I need to figure out what's left over. So 3 minus 0 is 3. 1 minus negative 1 is 2. Okay, just to double check, 2 minus 1 is 1. So now I need to look on the periodic table, find out what element is element number 2, and that is helium. Now we've seen helium as an alpha particle. Please note that this is not an alpha particle because the mass is different. This one has a mass of 3. The mass of the alpha particle is actually 4. Okay, so here we've got our final answer. Okay, determine the radioisotope that decays by beta emission into xenon 131. So this question is a little bit different. The xenon 131 is actually a product because it's saying what if it decays into xenon 131. We also know that it is a beta decay. So the xenon is now going to be a product. So xenon 131, I need to go to my periodic table to figure out what my atomic number is, and xenon is 54. We are told that it is a beta decay, and because it's a decay, that means the beta particle will be a product. So now I need to figure out what we started off with on the reactant side. So 131 plus 0 is 131. 54 minus 1 is 53. If you look on your periodic table, element number 53 is iodine. So this was our answer, or our original isotope. Okay, so we can see here what's happening. The next type of nuclear reaction is called nuclear fission. In nuclear fission, we take a very large radioactive isotope and it gets split into smaller ones. So fission means to divide. Usually in order for this to happen, it is bombarded by neutrons. So we saw when Chadwick discovered the neutron, he bombarded it with these small subatomic particles. That was a neutron that split it apart. So here's nuclear fission. I've got uranium-235, which is a very large radioactive isotope. It gets bombarded by a neutron. It makes it very unstable and then splits off into 2 smaller radioactive isotopes. In this case, krypton-92 and barium-141. Another product of this reaction will be some number of neutrons, depending on how it splits up. With this graphic here, you'll see that I'm starting off with the same uranium, but it can split off into different variations. This one split off into krypton and barium. This one split up into rubidium and cesium. This one xenon and strontium, or again, barium and krypton. So it all depends on how it's split up, that it can lead to different variations of isotopes that are created. So in this type of example, you are given a whole bunch of parts of the equation and you have to kind of figure out what's missing. So here I have uranium-235 is being bombarded with a neutron and it creates two smaller isotopes here. I need to figure out what is left over. Sorry. So uranium-235 plus one neutron produces, what do we have here? Bromine 87. And it produced 3 neutrons. Okay, we need to figure out what is missing here. So first of all, when we're doing this, just take a look at some of the notation. I have 3 neutrons. This 3 gets multiplied by the different particles within here. On this side of my equation, I need to add up what the superscripts are. So this gives me 236. And then I also need to add up what the subscripts are. So 92 and 0 gives me 92. On my product side, I have 87 plus 3. Okay, so 3 times 1 is 3, so that gives me 90. Here I have 35 plus 0. 3 times 0 is 0, so this gives me 35. Now I just need to do a subtraction. 236 minus 90 will give me this number. 92 minus 35 will give me that number. Okay, so when we look at this on here, what I end up getting is 146 and 57. In your notes, just please disregard this uranium. This here was a mistake. This should not be in there, and I will take that out from the actual slides. The last type of nuclear reaction is called nuclear fusion. Fusion is the opposite of fission. Fusion is when we take 2 small atoms and we fuse them together. So we have 2 light ones that make a heavier atom. This produces a lot of energy in the process. Finally, the last thing we're going to look at here is how radiation can affect you. So MREM is a unit that is used to measure the amount of radiation that something emits. So if you were to live next to a nuclear power plant, if you've seen the movie Chernobyl on Netflix, this is a great pseudo-documentary about what happened to all the people that live next to that power plant. If you live just next to a power plant, you have very low exposure. Now, that whole incident in the 80s was a completely different story because there was a leak of all of the radioactive material. In that case, you would be very much exposed to that, and they are still dealing with the after effects of that over 40 years later. Next, annual exposure from food and water is a little bit greater. If you've ever had a CAT scan, that is a lot. One of these boxes down here is your exposure during a flight, and then how much you need to be exposed to increase your risk of cancer.